Thank you, Siddhartha, and also CQST members here. It was, I'm very happy to give this talk. We are very neighbors in many regards. So the talk I will present today is based on my recent works on testing the coherent state description of gravitational radiation. So this is motivated by testing the question of addressing whether gravity has quantum mechanical characteristics, but we want to understand from a point of view of how we learned whether light has quantum mechanical properties. So essentially, the work is predominantly done during my postdoctoral time at Nordic Institute of Theoretical Physics, Nordita, Stockholm, Sweden, and works with Frank Wilczek and also with Igor Pikoski and Germain and Thomas, who were PhD students with Igor. So I will go through this in some steps, but I would begin. I would like to begin the talk by going back 100 years, when the beginning of quantum mechanics itself. You know that there were two important experiments that led to the formulation of quantum mechanics as we know it today. One is, of course, Planck's explanation for the black body radiation spectrum. So what is black body radiation spectrum? What was the experiment? So you have essentially something like a metallic box that you put in a hot oven, and there is a small hole in it. And from that hole, radiation is coming, and we have a spectrometer or something that measures the energy density between frequency nu and nu plus delta nu. And one does this experiment at different temperatures and across the different frequency ranges. And the idea, so there was one measured some spectrum in the experiment. Of course, not the entire spectrum was initially observed. And the efforts to understand this spectrum actually goes back to Kirchhoff in 1850s and so on. But Wilhelm Wien made some substantial progress, especially in the high frequency regime. He proposed a formula that tends to work very well in the high frequency regime. And then similarly, using contemporary electromagnetism and statistical mechanics arguments, Rayleigh jeans, they proposed a formula that worked very well at the low frequency regime. And Planck was essentially the person, he was originally very much motivated to understand the behavior at a high frequency regime and write down a theory. So Wilhelm Wien had a formula based on intuition and experiments and so on, but many people were trying to work on a theory to explain that. And one afternoon, actually, so Planck was also very convinced that Wilhelm Wien's result is a correct one. But then one afternoon, his colleagues came to his house for a coffee and then told him that they found evidence for black body radiation spectrum also at a low frequency regime. And then he immediately had this idea to write down a formula that works, that matches, takes both the Wilhelm Wien's result as the high frequency limit and then the Rayleigh jeans result at the low frequency limit, and wrote down a formula that worked across all frequency and temperature ranges. But of course, the genius of Planck was that in addition to writing down a fit for the black body radiation spectrum, he also wanted to explain it. So he came up with the idea that the walls of black bodies are essentially oscillators that produce radiation in discrete units proportional to the frequency of these oscillations. And with that and some statistical arguments, he was able to show that this black body radiation spectrum can be recovered. But the key insight was that he had to assume that the walls produce radiation in this discrete units proportional to the frequency. And incidentally, his original ideas were that maybe inside the block box, this black body box, light is still displayed by a continuous wave, that Maxwell's theory, according to Maxwell's theory, and so on. But then Einstein was independently working on trying to understand the black body radiation spectrum. And his idea was, he was also fascinated by Wilhelm Wien's result. And he was trying to do associate some statistical mechanics arguments. For example, he considered a box of high frequency light and estimated the entropy of this box of high frequency light. And he identified that this has similar structure comparable to a box of molecules entropy. So he was able to come up with an argument that light, not only how it is produced by these walls, that is Planck's original idea, but also in existence has some discrete nature that it exists as particles, especially at high frequencies. The light behaves as particles of discrete quanta proportional to the frequency, of course. And that proportionality constant is the Planck's constant. And with that, his genius was that he explained the photoelectric effect. The observation that, like, for example, when there is some light bulb shining on metal surfaces, you see photoelectrons emitted. And when you see one photoelectron emitted, there is some means to conclude that it is job done by a single photon. So he wrote down a simple relation to explain the photoelectric effect. And then Millikan and also Philip Leonard earlier and so on, they tested this to high accuracy. So in photoelectric effect, the key observation was that if you are below set the threshold frequency, even if you increase the intensity, you do not see any photoelectrons emitted. And above the threshold frequency or at the threshold frequency, if you increase the intensity, you see more number of electrons emitted. But the stopping voltage that you have to apply to stop the electrons from reaching the other electrode was the same. So it essentially shows that if you see one photoelectron emitted, that is job done by a single photon in the problem. So now if we, so these were pivotal experiments that led to the formulation of quantum mechanics as we know it today. But if you fast forward, there is a lot more we know about the quantum nature of light. For example, there is arguments that if you take a semi-classical limit of quantum electrodynamics, that also works to capture some of the essential features of the photoelectric effect. So, but then this semi-classical limit, where in experiments we treat light classically, is a convenient approximation in that it would show up in some violation. For example, energy conservation would be violated if you take the semi-classical approximation upon at the level of individual realizations of the experiment.
What parameters taken to be smaller?
So the semi-classical approximation is that we treat the amplitude of the field the same. So another way to look at it is the same as the classical amplitude. So the parameter that is assumed to be small is that, let's say we have a high intensity light driving an atom. It will absorb one photon from the field that is driving the atom. So the energy change for the field is of the order h bar omega, because one quantum is taken away from the field. But it's a high, large amplitude, such as something that we describe classically. Then the correction to the energy is something like plus or minus 1, h bar omega. And h bar is a small number, 10 raised to minus 30. So that we can neglect for more or less many classical experiments. This loss of one quantum of energy of the field can be neglected.
Is that what is quantum optics?
So in quantum optics, we have to account for it. So when we describe the optical radiation field quantum mechanically, that naturally accounts for the this loss and so on, and that is the full. So whenever we gain a photon on the atom matter state, the photon will be annihilated on the field sector. Yeah, but these issues were something that had bothered Einstein too. So, for example, in a letter to his friend Jacob Log in 1910, Einstein says, "At present, I have high hopes for solving the radiation problem, and that without light quanta. I am enormously curious how it will work out. One must renounce the energy principle in its present form." And then within 1 year, the Solvay meeting in 1911, Einstein says one can choose between the quantum structure of the radiation and the negation of an absolute validity of the energy conservation law. He asks who would have the courage to make a decision of this kind. And we will agree that the energy principle should be retained. And now, again, if we move a little bit forward, there are higher bars of testing whether a given radiation field is quantum or classical. For example, Bell inequality violation experiments are thought to be the only loophole-free test of non-classicality. And there are also experiments where we have observed sub-Poissonian counting statistics, and then there are Hongo-Mandel type experiments that probe the indistinguishability of photons, and then probing Wigner negativities in experiments, squeezing and non-classical correlations, and so on. But a lot of these interesting questions about whether radiation field is quantum or classical actually is rooted in this making semi-classical approximation, or asking the question that I have an experiment where I see some phenomenology, and do I need a quantum description for the radiation field to explain what I see in the experiment. Or in other words, what is the most natural theory that explains what I see, observe in the experiments. So this seamlessly going back and forth between quantum and classical description of radiation field. This is more formally done by the optical equivalence theorem, actually introduced by Sudarshan. So the idea is that if you have any linear field theory, for example, electromagnetism, or even linearized gravity, or acoustic waves or something, then we have a linear wave equation. And the solution can be expressed as sum over plane waves. And the correspondence between a quantum and classical description is identified by promoting the classical field amplitude to operators, classical field amplitudes to operators. And the way to go back to a classical description is by considering special class of states. These are coherent states. So when the radiation field is in a coherent state, we can take an expectation value of the field, and then this replaces these field amplitude operators with the eigenvalues essentially, because these coherent states are left and right eigenstates of creation and annihilation operators. So this going back and forth is essentially the one of the key insights from optical equivalence theorem. And one can also see that in a precise sense, this coherent states give well-defined values for the field amplitude operators. For example, yeah. So the theorem is twofold. So one is that we can go between a classical and quantum description of a radiation field, and the classical limit where we describe the field with classical amplitudes corresponds to considering the quantum radiation field in a coherent state.
That's more like an axiom than
Yeah, it's an axiom, but it's a theorem aspect of it. Maybe I would say that there is this. How now one can ask, how do I compute expectation values of operators using this, and there's a product of operators and so on. So then there's this normal ordering comes and then tells that in the coherent state description, I can assume certain ordering. The result that I obtain using the normal ordered representation in the operator form is obtained by an appropriate ensemble average over coherent states with a P function. So I'll come to that later. But at the heart of it is this idea. So let's say we take if two quantum mechanical states. One is a coherent state, one is a Fock state. And for both states, we can ask what is the average field amplitude. You'll see that for coherent state, the average field amplitude is well defined. It's some alpha and alpha star in front of plus positive and negative frequency components. But for a Fock state, this even if it has the same average number of photons as the coherent state that we consider, it has a zero amplitude. So you immediately see that a Fock state in quantum theory does not directly map to the corresponding average field that we want to describe. So this is very accurately captured, on the other hand, by the coherent state in the quantum theory. And how do you make it even a little bit more precise? So let's say we want to evaluate the variance of the field amplitude operators. These are non-Hermitian operators. But let's say we make a definition of the variance, which is the average of the square minus the square of the average. You'll find that for if the radiation field is in a coherent state, these variances are zero for a coherent state. So in that sense also, this coherent states give well-defined classical amplitudes that the corresponding classical theory describes. Yeah.
So also it should have like time independent kind of property, right? So these things will hold irrespective of the time that kind of thing.
Yeah, it will hold independent of the time.
And then it will depend on the Hamiltonian also.
The dynamics also, yes.
So if you have say not known dynamic, then
Yeah.
that kind of analogy is not work so well, right?
No, exactly. So this is true. And this is one way to test whether a quantum description is appropriate or not. Because when we use the corresponding time-dependent quantum theory, and let's say there is a Hamiltonian which is quadratic or something, it will introduce squeezing kind of effects. And that will introduce additional noise in the problem. So that one could see in an experiment. But if we use a theory where there is no quantum theory, so there is no squeezing comes in, just the amplitudes modify, then there won't be this excess noise that one would see in the experiment.
Yeah, because we have seen like if I generally master, so if I if I write a dynamics in terms of master equation,
Yeah.
then these are not the minimum uncertainty state. So none of these would exist.
Yeah. So if it is simple, just say A or A dagger, the Lindblad operators, I think just A, then this coherent states will remain coherent states under this dynamic.
Yeah, it's only if I don't write Lindblad. If I write general master equation, then there is a
Yeah. It's no question. Is there a question on that?
There was a thing.
Okay, I will do. Yeah, so then it makes it quite interesting to ask the question whether the radiation field is in a coherent state or not. Because to leading order, this is a nice way to test whether there are quantum, a classical, a semi-classical, or classical description for the field is adequate, or we want to go to a quantum description. So how do we test that? So for that, we consider, I will first present a generic approach. So we consider to a detector, a harmonic oscillator as a detector interacting with the radiation field. And we make this a linear interaction. And then we make the rotating wave approximation and so on. And then we can write down a simple interaction Hamiltonian of this type. We also make the Markovian approximation for the detector that different detector modes at different times commute, essentially. And we can ask the question, so we can also simplify this Hamiltonian, for example, considering a time averaged detector mode. So that D is the detector mode and A is the field. So I also made an effective single mode approximation for the radiation field. So typically there will be a number of modes about the resonant frequency of the detector that are incoming, but we can go to an effective single mode approximation where we replace the coupling by the square root of the spontaneous emission rate, essentially. So this can be shown. This is essentially how we derive this Fermi golden rule rates, and that we have to average over the field about the resonant frequency, and one can show that equivalently this corresponds to describing an effective single mode coupled to the detector with a modified coupling which corresponds to the square root of the spontaneous emission rate. So that is an intrinsic property of the detector. So it tells the probability of the detector going from an excited state to ground state by spontaneously emitting a quanta that we want to detect. What is the rate of? What is the spontaneous emission rate? So we can write down a time evolution operator, but we can say that it can be equally described by a time average detector mode. But then effective Hamiltonian has this particular structure, the square root gamma naught delta t. And these time average modes essentially satisfy the commutation relation that d b dagger equal to 1. So now one can ask how does the state evolve when the radiation field is in a coherent state and the detector is initially in the vacuum state. So this is essentially one coherent state and the vacuum state time evolved under this resonant interaction. What you see is that the coherent state amplitude slightly decreases and the amplitude of the detector slightly increases, goes like sine. Now one can also ask what happens for a generic quantum state of the radiation field. So to compute that, one can use this Sudarshan-Glover P representation. So any arbitrary quantum state of the radiation field can be written as an ensemble over coherent states. It looks like a mixed state, but it's actually, it can also be done for pure states because coherent states form an over-complete pieces. So one can write down the generic state of the radiation field as such. And now we can act this time evolution member by member. And we see that the generic state of the detector and the radiation field evolves in this way. So now one can ask what are the different counting statistics that one observes in experiment. This corresponds to measuring different number in the detector. So that one can compute. Essentially, you know that in coherent states, the probabilities are the states levels are occupied as a Poissonian distribution. So a Poissonian distribution comes, but it's also convoluted with the P function of the radiation field. In fact, if you take, so this it's a simple straightforward derivation by considering two harmonic oscillators. But if you look at Mandel's theory, one gets the linearized approximation of this as the outcome with considering photoelectrons emitted in finite time and so on, doing perturbation theory multiple times. So yeah, so what do we have now is the probability distribution of seeing n jumps or n level occupied in the detector, which initially started in the ground state. And that has this particular form. So it's a probability distribution. So we can compute the mean and variance of this probability distribution. So if we compute the mean, the average number of clicks, so I would call these jumps on the detector now onwards clicks. So if we compute the average number of clicks, what we find is that, and it is sum over NPN essentially, and we find that that is gamma naught delta T times the average number of quanta in the radiation field. So this is an interesting point. So what this identifies this gamma naught delta T as the quantum to click conversion efficiency for our detector. And there is one parameter that describes it, it is gamma, and that is the spontaneous emission rate of the detector for the radiation quantum we want to detect. So this essentially encapsulates this idea that in quantum optics, we often say good emitters are also good detectors. If we have a higher spontaneous emission rate, my detector is a good detector because the quantum to click conversion efficiency can be high. And we also hear often that we have good single photon detectors. What it means is that this quantity, gamma naught delta T, can be of order 1 fundamentally for single photon detectors and so on. So now one can also compute what is the variance of clicks. So that a similar calculation can be done, and we'll see that it is the average number of clicks plus something. So there's the efficiency square times Mandel Q parameter times the average number of quanta in the field. So Mandel Q is essentially the variance minus mean over mean for the field state. So if it is between -1 and 0, we'll say that the radiation field is subpoissonian. So a Fox state has well-defined a number state has a well-defined number. So its variance goes to 0. So we get Q equal to -1. And Q is equal to 0 for a coherent state. It is Poissonian. So mean is equal to variance. So then the difference goes to 0. And Q is greater than 0 for super Poissonian. Termer state is an example of the super Poissonian state. But what we see is that the variance that we see in the detector, so there are two things, the variance of the quantum state of the radiation field, and then we want to infer that using a detector. So we see some variance of counts in the detector, and they are related by these things. So for example, when the one thing can immediately note that if the radiation field is in a coherent state, the variance equal to mean also on the detector. So whatever count we see, it will also be Poissonian on the detector. So here is some example. So if the radiation field is in a coherent state, like I said, we will see that the variance Q is equal to 0. Therefore, the average number of counts we get is also the variance of counts we see in our detector. Now we can consider another example when the radiation field is in a thermal state. For a thermal state, this Mandel Q is actually proportional to the average number of quanta in the field itself. And therefore, the variance that we see will also be super Poissonian. But note that, of course, it is the efficiency square comes in. So the deviation from Poissonian part. So this first part is, of course, the average number of clicks. So if it was equal, this would be Poissonian. But there is an extra term proportional to Mandel Q, and that that is actually substantial. It actually goes like square of the average number of clicks we see.
That also is the laser.
Okay. Okay. So we can also evaluate for some non-trivial state, something like a highly squeezed vacuum state, and we can see that the excess noise that we would see from Poisson actually goes like 2 times the intensity of the field. So if we let's say in some cases we can do full counting statistics, we can use this counting statistics to infer or discriminate between different quantum states of the radiation field. And for Poissonian states, for example, this the deviation from the mean actually goes like proportional to the intensity. Not there's still an efficiency square. So the efficiency is bad. That the hope of seeing Poissonian statistics in our detector is also low. That is the essential idea. Yeah, so we'll see different statistics essentially for different quantum states of the radiation field. And if we can do full global counting statistics, we can tell apart between what is the state of the radiation field. But then, often cases, the example of gravitational radiation that I'll give as an example, there is not so much hope of doing the full counting statistics. Let's say we have a detector that hardly clicks ever. So maybe there is some hope of seeing 1 click and maybe 2 clicks and do some compute P0, P1 and so on, but not much more than that. the question is, can we still say something about the quantum state of the radiation field with such very bad or weakly coupled detectors? So what is interesting is that you know that coherent states, for example, have Poissonian counting statistics. This Poissonian statistics actually obeys rigid relations between the probability of seeing no click or no click, zero occupation, one occupation, and two occupation. For example,
what are the alternatives that it looks like that you are trying to infer the state by like photon counting detectors?
Yeah. So there is
something else as well, right?
Yeah. So we'll also do homodyne and heterodyne in the later. I will give some example and also correlations between different detectors. So instead of measuring number, if we measure in the position basis of the detector, that corresponds to homodyne. If we do coherent state basis, that corresponds to heterodyne. Yeah, so for a Poissonian statistics, if you take 2 times P0 times P2, that is equal to P1 square. So one can ask, and this is the satisfied for the state, but the same relation is also satisfied for the counts that we receive. The radiation field is in a coherent state because that is also Poisson. So one can ask for a coherent state, if we take the probability of 0 click times probability of 2 clicks divided by probability of 1 click square multiplied by 2, we get the answer equal to 1.
So this is just one condition. There are more conditions.
There are more conditions. Yeah. So then similarly, if you take a thermal state, so assume that the radiation field is in a thermal state, and then we compute the ratio 2 times P0 times P2 divided by P1 square for whatever we see in the detector. Remember, it was this convoluted with the P function and so on. So we'll get the answer 2 actually. Now, if we do this for a highly squeezed vacuum state, and we look at this ratio 2 times P0 times P2 divided by P1 square, we get the answer equal to 3. And in fact, if we now do it for a number state, so the field is in a number state, and compute the ratio 2 times P0 times P2 divided by P1 square, we get 1 minus 1 over n. So in the limit of large n, so it's a highly occupied state, this ratio goes to 1. So that tells that we cannot discriminate from a coherent state if the field has high intensity using this ratio test. But generically, what is this 1, 2, 3 numbers? So actually, this 2 times P0 P2 by P1 square, this is 1 plus Q over n. Q is a Mandel Q parameter. And that is actually what is known as the second order coherence function for the radiation field. So we are able to probe the second order coherence function by just looking at the lowest order click probabilities.
So how one can derive these relations?
So one can do this perturbatively. So take a field, consider the exact time evolution, and then do perturbatively.
And this is true for arbitrary state.
This is true for arbitrary state. So one can show that the ratio, if you take it to exact same model, it will converge to this one.
What is the perturbation? The coupling.
The coupling, yeah. And so for thermal state and so on, you can actually see it from the exact result itself. So you can just, even also for coherent state, it's really.
So what do you mean by highly vacuum states?
So it's the radiation field is, let's say, in the vacuum state, and somehow you squeeze it. So apply the squeezing operator, e raised to a dagger square. So and in fact, for a generic state of the radiation Gaussian state, which is a displaced squeezed thermal state, one can actually show that this ratio has this following structure, and it will reduce to the appropriate limits for displaced state, vacuum state, and thermal state, and so on. So this essentially there is some variability, but the variability is basically in the large intensity limit is between 1 to 3.
So how do we reach it? So what are the cases here? So for example, if R is 1, then
it is coherent state, and R equal to 2 is thermal state. R equal to 2 is highly squeezed vacuum. Yeah.
So for other state, it will not be 1.
Yeah. So the generic result is it is 1 plus Q over n, and it is for any state of
say this kind only parameters evidence can, so that will not be able to distinguish the state.
It will not. So it can still tell if it is a coherent state or not. So that is the one of the main insights.
Obvious from here, right? This number depends on Q and the expectation of N.
Yeah, but we know Q for a radiation field state. For example, if it is in a thermal state, it goes like N. So therefore, 1 plus 1 over 1 equal to 2. Yeah. And for a squeezed vacuum state, it is 1 plus the Q goes like 2n. So it becomes 1 plus 2 equal to 3. I mean, highly squeezed vacuum state. It approaches that value. The scale goes like cos hyperbolic r plus 1. Yes, yeah.
So I'm like curious that if people use this kind of relation to tell apart whether the source was or not.
Yeah, not the ratio test actually. So, but people do use other ways to probe the second order coherence function. But this we propose that. Yeah, so. But it's also an interesting thing because there are some cases like this when this ratio or the second order coherence function equal to 3. Probably there are no experiments that have probed it for light because this squeezed vacuum state is maybe difficult to construct and probe is G2 is even difficult. So I had some conversations where people told me that maybe it is not experimentally tested. So this might also be a nice way to test it in experiment. We assume the weak coupling. Yeah, so now I will come to application to gravitational radiation. So what is the interesting problem here? So like we started the talk with observing matter and light, exchanging energy in discrete unit was an important first step in formulating the quantum theory of light. So one can ask a similar question, whether we can detect a graviton as an exchange of energy in discrete units between matter and gravitational radiation. So how do we even detect gravitational radiation? So the essential idea is that whenever gravitational wave passes through, it changes the distance between 2 points. So we use this to detect them at LIGO. So in LIGO, we have very high sensitivity so that we can measure displacements delta L over L. L is say 4 kilometer or something, which is of the order of 10 raised to minus 22. So one can measure 10 raised to minus 18 or 10 raised to minus 19 meter small displacements with this interferometric technique. But it also means that if I take a hydrogen atom and ask what happens when a gravitational radiation passes through, it also modulates the relative distance between the electron and proton in the hydrogen atom. So when gravitational wave passes through, these relative distances are the ones that would change all the, and then it is almost like a quadrupolar oscillator. And we also know that gravitational radiation, all the sources of gravitational radiation are also dynamic quadrupole things that change the quadrupole moment dynamically when the merger event happens and so on. So the detectors should also have this kind of quadrupole nature. So, and then what is the quantum mechanics of gravitational radiation that we are talking about? So, of course, there is a lot of discussions about what is the full quantum theory of gravity, but a generic idea is that in the linearized low energy regime, it should reduce to a linear field theory where gravitational radiation is populated by h bar omega gravitons. And this, we also know that the wave equation if we fix the gauge conditions, it reduces to a simple wave equation, like the plane wave equation. Solutions are plane waves. And then there are also, we start with 10 degrees of freedom, and then we put all the gauge fixing conditions. We'll be left with 2 degrees of freedom, which are the plus and cross polarization of the gravitational radiation. And these gravitational waves are conveniently represented in this what is known as TT gauge. But then how they interact with matter, it is better understood in what is known as a local inertial frame. So one can define what is one has to compute the interaction Hamiltonian. So that follows from the definition of the energy momentum tensor as the variation of the matter action with respect to the material. So essentially computing that, one gets a quadratic Hamiltonian, for example, if we consider electron in the hydrogen atom. So we see that this is a quadratic type of interaction. That is this essentially going back to this quadrupole oscillator type of behavior when the gravitational wave passes through.
So metric couples with the matter.
Metric couples with the matter, yeah. And to a non-zero quadrupole oscillation type. Yeah. And then people have asked, does this have experimental consequences? So do we see any prospects of detecting quantum nature of gravity through this kind of thing? So if you look at Weinberg's textbook on gravitation and cosmology, there's a section where he asks the question, let's say I prepare a hydrogen atom in an excited state with a non-zero quadrupolar transition moment to another state. What is the probability that the system will de-excite by emitting a graviton. So if you remember, if we were asking this question for light, we will ask what is the probability that a system in an excited state go to the ground to a lower energy state with a non-zero dipolar coupling, because light couples to dipole transitions, but gravity couples to quadrupolar transitions. There's also no two different kind of charges in gravity, it's all the same mass. Right? So Weinberg asked this question, but he found that it takes 10 raised to 40 seconds for a hydrogen atom prepared in an excited state to decay by emitting a graviton spontaneously and going to the ground state. And that is actually, the age of the universe is approximately 10 raised to 18 seconds. So it takes much more than the age of the universe for a hydrogen atom in an excited state to go to the ground state by emitting a graviton. So he says that actually he estimated 10 raised to 44 seconds, but then later Born and Altman found some calculation mistakes, but it's still 10 raised to 40 seconds. This is the rate inverse of that. But he correctly says, needless to say, there is no chance of seeing such a transition. Similarly, Dyson, he had asked the question whether LIGO, which is our current best classical detector for classical gravitational radiation, can we see single graviton signatures using LIGO? And he essentially asked the question, we know that the sensitivity that we have is something like 10 raised to minus 20. So one can compute how many gravitons does a gravitational radiation with this strain amplitude correspond to. So how do we do that? We know the energy density of the radiation and divide that with the energy density, assuming a single graviton, so h bar omega in his reduced volume cube box. So then he obtains a number which is 10 raised to 36. So the radiation field that our LIGO currently sees, it has 10 raised to 36 gravitons in local mode volume. So, but then his argument was that in order to see this single graviton strain amplitudes, we have to improve the sensitivity by 10 raised to 36 orders of magnitude. So he also said that there is no hope of seeing such a, you cannot improve LIGO sensitivity by that huge amount. So there is no hope of seeing such a transition. He also estimated, similar to Weinberg, what is the atomic transition, cross-section probabilities, and so on, and he gets Planck area square, which is again a tiny number. So there is no hope of seeing this section. I mean, the detection of the graviton with atoms or LIGO. So in this, but in this recent work, we proposed a way to detect single gravitons, and it is important to understand how do we go beyond these ideas by people have told it is not possible. So for example, to counter what Dyson said, it is one thing we learned from the photoelectric effect is that we actually do not need single photons to come to infer the exchange of a single photon with single quanta. Essentially, we have something like light bulb shining on metal surfaces, which kicks out electron, and there are means to conclude that when we see a single photon ejected, it's a job done by a single photon. And LIGO, after all, need not be the best detector to do the job. LIGO is effectively measuring these position displacements. So if we want to detect a quantum of energy, we have to measure the number or energy operator on the detector side. So LIGO may not be currently, at least in its mode of operation, it's not engineered to detect energy exchanges. Then the other thing is, of course, Weinberg was looking at a system, atom, which can produce such a discrete response, but the cross sections and so on that he estimated were extremely tiny. So we looked at essentially massive quantum systems, so systems that are more massive and can have therefore a larger quadrupole moment, and then essentially a collective effect. So if there are more atoms, they can collectively contribute to these scattering processes. And then we also consider LIGO band events. So then we know that there are 10 raised to 36 gravitons that are incoming in every local mode volume based on the events that we have already observed. And then we combine that with this quantum sensing of energy or the number operator of some modes to detect that. So we essentially go back to an older idea by Weber, but with a quantum twist. So some of you might have heard the name Weber. He was a pioneer in gravitational wave astronomy. So even before the time when people were debating whether gravitational waves truly exist or not, or could get rid of them by doing some gauge fixing, he was the person who came up with the idea of taking a huge aluminum cylinder and put a piezoelectric through it to measure the tidal force induced changes. He proposed a detector, he built those detectors, and he even had made claims of detecting gravitational radiation with this technique. Of course, his idea was to detect classical gravitational waves by measuring these position displacements induced by tidal forces. But there was not enough corroborating evidence to substantiate his claims. And eventually, LIGO, which is a conceptually slightly different way of detecting gravitational wave, came along in 2015, led to the first detection of gravitational waves. So what we do is that we take consider a similar system and quantize the system. So if you think about such a giant bar, we can think about it's an array of atoms, and then we want to understand that when gravitational wave passes through, each of these atoms are going to oscillate. But then the system also has collective modes. So one can ask what are the acoustic modes of the system, and then each of these acoustic modes are collective modes of vibration of these atoms in the lattice, and they each of them have mass m/2, where m is the total mass of the bar. So it's almost like a basis change instead of looking at the individual atom point of view, we go to this collective acoustic modes of the system. And then if we evaluate the coupling to gravitational radiation for this,
so what physical system
so something like a huge aluminum cylinder, let's say we want to quantize that. So people have done it at smaller scales. So let's say mechanical oscillator and so on. So very small systems, but these systems have acoustic modes, sound modes of vibration. Which elastic yeah. Crystal. That's exactly. This is the idea. But I will show you what are the parameter ranges that we want to do this experiment on. And depending on the frequency band we are interested in, it can be small or large, essentially. Yeah, but now we can essentially compute the coupling to gravitational radiation. You see that both of them are actually quadrupole in nature because the first term has a length factor that comes out. But the leading order coupling actually increases with the mass of the bar detector as well as the length of the bar detector. So with this, with that one can now ask how do the rates modify. So if you look at the spontaneous emission rate, which was 10 raised to minus 40 for a hydrogen atom, we find that it's actually now 10 raised to minus 33 for a 8,000 kilogram niobium cylinder with the speed of sound and so on. It is 8 orders or 7 orders of magnitude improvement, but still it is tiny. But instead, if we look at the stimulated absorption rate, so this photoelectron emission in photoelectric effect, is the stimulated absorption of the photon. So we see that it actually improves by the intensity of the incoming radiation field. So one can, in principle, get stimulated absorption rate of the order of essentially 1 hertz, which means if a gravitational radiation in the LIGO band comes, and if we prepare aluminum cylinder by using aluminum, because Weber was using aluminum, so one would get a response of, in principle, let's say we do the ideal experiment, we can have a graviton exchange or a graviton absorbed and emitted at a rate of 1 hertz or 1 per second.
Why would Weber do that?
Because also has to do with the material properties. Maybe one has to get very good crystal and so on. And so you reduce a lot of noise, and maybe aluminum was also available. Yeah, so then, so this is substantial, but it's also not very surprising. What have we done is that we've taken a system which Weber was also hoping to have a response to classical gravitational radiation.
Sorry, I got distracted. So why did Weber use aluminum? It has to do with material.
It has to do with material properties, and probably it was also you want to get one has to measure the acoustic modes of the system, and also want to create resonances in certain windows. So ideally the kind of thing that after all, what is the speed of sound of the material and so on, and then that gives the resonance frequencies of the modes, and then also one would want clean samples. That determines the size of the bar. The size of the bar is determined by mass and length or by what frequency we want. So essentially the fundamental mode frequency is something like 5 Bs over n. So here is the protocol to infer single graviton exchange event. So let's say we have some radiation fields coming in the some frequency, let's say kilohertz LIGO event. So LIGO would see a classical gravitational signal. So let's say we have a bar detector that is prepared in the ground state. So we have to cool this detector to its quantum mechanical ground state, which means not every mode has to be cooled, but the one mode that the resonant frequency mode that we are interested in have to be cooled to the ground state. And then if everything works well according to theory, then we will see a quantum jump happening from the zero to the first excited state of the bar detector. And similar to the photoelectric effect, we would call this a gravitophononic effect because it's a gravitational radiation inducing a phonon-like excitation in the bar detector. And this will alone will not say prove quantum theory of gravity, but this will be an indication just like the photoelectric indication for the existence of photons. But then I also told you about more things one can do, the statistics of radiation.
So can you explain this equation, please?
Yeah, so this is essentially the transition probability from
Yeah.
0 to 1 using that interaction Hamiltonian. And
So how this equation is coming? Can you just?
yes. So this equation comes from writing down the semi-classical interaction Hamiltonian.
Okay.
So essentially, this is something like A plus A dagger times the amplitude of the field. And then that is the interaction Hamiltonian. Then we do a perturbation expansion, assuming the field is in a, so let's say we can start with the full quantum theory. So B plus B dagger for the field and A plus A dagger for the matter. And then start the matter in the ground state, the detector mode in the ground state, the field in a coherent state. We ask the question, what is the probability that the field matter goes to first excited state? So you take sandwich from 1 alpha, the semi-classical approximation, then take mode square. And then we make this rotating wave approximation. So we throw away these counter rotating terms. And then you can show that this goes to a sinc function. Actually, it also comes down the same way in quantum optics atom interactions. Yeah, so but like I said, we have the possibility of doing statistics. So for example, if we were to ask
Another question.
Yeah.
Does phonon is detectable?
Phonon is detectable. So we have experiments that have detected single phonon.
Okay.
Yeah, and maybe at lower masses, like micrograms and so on. But phonon we have detected. So yes, then the same theory of counting statistics of seeing n number of jumps in some finite time applies. So if the gravitational radiation is in different quantum mechanical state, the probability distribution of counts that we see in our detector will also be different. And in fact, one can ask, say, make some rough estimates. Let's say the spontaneous emission rate of the bar detector is 10 raised to minus 33 per second. And then let's assume that there are 10 raised to 36 number of gravitons are coming, corresponds to gravitational waves in the LIGO band. And let's say we are measuring for a duration of 1 millisecond. Then we roughly see that the number of clicks that we get, which is gamma naught delta T times the average number of quanta, efficiency times the number of field quanta, is of order 1. So we have some hope of seeing 1 click in a perfect detector which has this spontaneous emission rate. The small spontaneous emission rate is essentially compensated by the large influx of gravitons. And then one can also compute, let's say for different quantum mechanical state, how do the noise look like? So by heuristically doing the same calculation, we see that if the field is in a coherent state, the noise will also be of order 1. But if the field is in a thermal state, this noise will be roughly, or the excess noise will be roughly of order, or the noise will be of order 2. And then if the field is in a highly squeezed vacuum state, the noise will be roughly of order 3, essentially. But we may not have the hope of seeing these experiments. There are some proposed detectors now, but they are not detecting gravitons. So one can ask, this is a very difficult problem. So let's say we don't see so many clicks, but we only have the hope of seeing a few number of clicks. What can we do? So we can apply this ratio test and then show that, for example, if you compare the ratio of 2 times P0 times P1 square, it will give answer 1 if the radiation field is in a coherent state. It will give answer 2 if the radiation field is in a thermal state. And it will give us answer 3 for the radiation field. In this case, gravitational radiation is in a highly squeezed vacuum state. Yeah, and then coming back to your question, one could also do a test where instead of doing counting statistics, we measure in some other basis. For example, one can do quadrature measurements. So in this case, one can compute what is the variance of quadratures that we see. And that will also have some intrinsic quadrature of the radiation field, that is the half that comes in the beginning. To that, there is a contribution from the field noise itself. So the delta P square is the variance of the field. And this will also be like if the radiation field is in a coherent state, this answer will be the field quadrature variances will be also be equal to half. So you won't see any excess noise over the detector's intrinsic vacuum noise. But if let's say the radiation field is in a fog state, remember fog state is special because it is very difficult to discriminate from a coherent state using the ratio test that I talked about previously. But here they will show a huge variance. So it's something that goes like n plus half. So then one would in principle see of order 1 unity, I mean order 1 difference from the vacuum noise of the detector. And one could also do some heterodyne power measurements, and that would also see different noise signatures as a more comparable to counting statistics. So what is interesting here is that these are, one could say, these different detection strategies give complementary information about the radiation field. So certain states have more noise when you measure the phase of those states. Certain states have more noise if you measure the number operated in these states. So this, if you see complementary features in measurements of phase versus number, it is actually probing the number to phase commutation relations for the field. For some aspect of non-commutativity of the field quadratures, which is also a proof. If you see, it will also indicate quantum theory is the most appropriate theory to describe the radiation field in these experiments. So one could also do detector cross correlation. So as an example, let's say you take two detectors and then measure the number cross correlations. So it's almost like, let's say there is rain happening and two people are counting raindrops, and it's Poissonian distribution. And if you look at what is the correlation of counts, you will get an answer 0. But if similarly, if the radiation field is in a coherent state, and if there are two detectors, both of them measuring counts, and if you measure the cross correlations between n1, n2 average minus average of n1 times average of n2, you will get answer 0. But if it is in some interesting quantum mechanical states, actually this cross correlation is not equal to 0. It goes like efficiency square times q times n. So for some states, this can be of order 1. It's almost like a 0 versus 1 test of whether the radiation field is in a coherent state or not. And there are also similar complementary measurements possible by doing cross correlations between different detection strategies like homodyne, heterodyne, and so on. So here comes some parameter regimes for the detector that one would ideally want. So let's say if we have a beryllium detector of something like 15 kilogram, I think, yeah, 15 kilogram, then one could actually map this one, that GW170817 is a neutron star merger event. So if we look for those parameters, so they actually kind of give monochromatic gravitational radiation for long duration. So for that, if we had a beryllium detector ground state cooled and we monitor its 100 Hertz frequency mode, there is hope of seeing this quantum jumps happening in the detector. And then you also see that there are some high frequency ranges for which the proposed detector mass can be even 10 gram and so on. But these high frequency ranges, we don't have so much known sources of gravitational radiation. So it's also speculative. So LIGO, for example, may not see because the noise is also high. But in the future, there is, let's say we start detecting high frequency gravitational radiation. There is also hope of having smaller detectors which could, in principle, respond. And this is a comparison in terms of so there are these resonant bar detectors. I told Weber had this original idea of detecting classical gravitational waves using a classical detection strategy. There were still some detectors in operation, still looking for these classical signals, mainly now at high frequencies because you can have smaller detectors to do the job. But for these detection strategies that I discussed, we need to make sure that the thermal noise jumps introduced by thermal background is smaller rate compared to jumps introduced by the gravitational radiation. So that requires us to have quality factors and temperatures, lower temperatures, somewhat 2 orders of magnitude better than what these current detectors have achieved. And of course, they are all kind of measuring the position displacements classically. So we want them to change to measuring the number operator also. And that could also be a challenging part. So also in terms of cooling larger systems, so it's very hard to put this in a dilution refrigerator and cool to 1 millikelvin temperature can work and so on. But sometimes these feedback cooling techniques can be useful. So for example, there is a nice experiment in LIGO where they kind of constructed an effective 10 kilogram mode out of center of mass motion of several things. It's a center of mass mode, but they claim that they have cooled it down to n equal to 10 Fock state. So in LIGO, people call this experiment cooling an elephant to the quantum ground state. So it's a challenging, but in principle, there could be clever ways of achieving such a cooling strategies. Yeah, so with that, I will conclude. So what I talked about the idea of probing quantum ecoherence. So this is motivated by looking for experiments where one see a difference from a classical description of the radiation field. So that can be formulated as testing whether the radiation field is in a coherent state or not. And one can have different tests. In particular, one could have, for a weakly coupled field, one can have this ratio test that you take the ratio of 2 P2 P0 by P1 square. You can actually prove the second order coherence function of the radiation field. And then this is all work with Professor Wilczek. And even what is interesting is that in the seemingly classical limit, let's say these results might also be applicable to test if optical radiation is quantum mechanical in the seemingly classical limit of large N by considering a weakly coupled detector. So we constrain the detector to have a very weak response. So construct bad detectors out of good ones, and then one could test these kind of quantumness of in the seemingly classical limit of radiation fields. And in particular, these results are applicable to test the quantum nature of gravitational radiation, in particular to probe gravitons in the true propagating degrees of freedom of gravity, whether they have quantum signatures. And then there are also these complementary detection strategies that can actually probe complementary features of the radiation field and further inform or give more substantial arguments to prove whether we should use quantum mechanics to displace gravitational radiation or not. So with that, I will conclude. Thank you.